Hello, quick video on factor theorem and how it works. We may well have a high order polynomial which we need to sketch or find the roots of or find the factors, and the factor theorem is really useful for this. Here's a sort of polynomial we might be looking at. It's got higher power of x to the 5, so there's no easy way to find the factors, but the factor theorem will help us along with trial and improvement to find the roots and the factors, and we could go on from that to algebraic division and other methods of finding less obvious factors. So let's have a look at why this works. At GCSE we spent a lot of time factorising quadratics. So we would take a quadratic like that, expression x squared plus 2x minus 3, and we factorise it into this expression on the right, factorising being in the bracket, something multiplied by something. And we did that, didn't we, by finding two numbers, these two numbers here, they're going to multiply together to get that, and if we add the two numbers we'd get the 2. So we could then use this method to solve the quadratic, couldn't we? So we took the expression and we set it and find out when it's going to be equal to 0, and we replaced the expression with our factored version of it, and that must be equal to 0. So that tells us that one or other of these brackets must be 0, because a number times by 0 equals 0, and two numbers that are not 0 multiplied together don't make 0, do they? So that meant that either the first bracket is 0 or the second bracket is 0. One of these factors, yeah? And if x minus 1 is 0 equals 0, then x must equal 1. And if x plus 3 is 0, then x must equal minus 3. And all of this relies on the fact that if we take any number and we multiply it by 0, we're going to get 0. And in most general terms, so a number times by 0 equals 0, or 0 times a number equals 0. Now we can extend that idea in principle to having more and higher order polynomial by thinking about it as just a whole load of brackets multiplied together. Yeah, each of these brackets is a factor. So if we multiplied out the bracket, we'd have a huge polynomial, high order polynomial. But if we say that that equals 0, then one of these brackets must equal 0. Either the first one's going to equal 0, or the second one, or the third one, or the fourth, or the last one, yeah, and any in between. So therefore, either x equals 1, or x equals 2, or x equals 3, or minus 3, or x equals minus 7. And if we wrote that in function form, that means that the function of 1 equals 0. If we put the value in, or the function x equals 2 equals 0, or the function at x equals minus 3 equals 0, or lastly the function at x equals minus 7 equals 0. So can we see here that's telling us why, in the most general terms, that if x minus 1 is a factor, then f to the 1 must equal 0, and that goes all the way through. So for any value, if we call that generalized alpha, then if f the alpha equals 0, then x minus alpha must be a factor. So let's have a look at that as a generalized proof. If we start with our function as we were looking at above, there was our f of x, and we believe x minus a is a factor, then we could put all the rest of the junk, all the other brackets in here. This is just the g of x is just a whole load of brackets. We don't know what's in those, yeah? And if we set the value of x equals a, then we'd write that on the left, wouldn't we, in that format, f of alpha, and this is going to be, this bracket is going to be alpha take away alpha, which is going to be 0, and 0 times whatever this number is always 0, yeah? So there we can quickly see that if f of alpha is 0, we can go backwards and show therefore that x minus alpha is a factor. Why can't it be, could there be any other circumstances where f minus alpha equals 0 and it's not a factor? Well, let's just have a look. Let's have this example here. Here's a quadratic. There's x minus 2, here each of the brackets, aren't there? So for each one of those, is a factor. But if I put in, say, f equals 1, if I wanted to see whether x minus 1 was a factor, and I put in therefore x equals 1, I wouldn't get 0 for the first one, I wouldn't get 0 for the second bracket, or for the third, or for the fourth. Here are their values. And therefore, if I multiply them together, I'm going to get something that's non-zero. So if none of these brackets are 0, then the product of them cannot be 0. Yeah. So it can't be the other way around. So if f of alpha, any number, specific number equals 0, that's only going to be true if and only if x minus alpha is a factor. Yeah, can't happen any other way, because otherwise we'd have a non-zero product, wouldn't we? Okay, let's have a quick look at an example then. Let's have a look at this long polynomial. And we're going to use trial and improvement first to try and find a factor. What we do is try and find the root. So we're going to put numbers, values of x in there, and we'll see if we get one that comes to 0. So usually we'd start off with x equals 0. And f of x equals 0 is, having a look at the terms, is 0, minus 0, plus 0, minus 0, plus 0, minus 1. So the answer is minus 1. So is that a root? No, because it's not to 0. If I try x equals 1, I get 1 minus 5 plus 3 minus 2 plus 4 minus 1, which equals 0. Bang. So that's a root. And if I could carry on looking for all 5 of them. I'll just try one, which, the next one up, x equals 2. Well, if I do that, I get a horrible number of minus 25. So there's no obvious other root. So I've got one here. I know that when x equals 1, f of 1 equals 0. Yeah. There we go. So I've found one. And given the factor theorem, if f of 1 equals 0, therefore x minus 1 is a factor of f of x. Now we can either continue looking for the others, who trial and improvement, or so we could do that until we find all 5. So we should be looking for 5 of them there. And they may not be obvious ones. Or we could just think about rewriting what we've just done. So our f of x now equals x minus 1 times g of x. And we could then use other methods like algebraic division or grid method to find out what g of x is and then go through the factors of that. Okay, so to summarise, factor theorem states if we have a polynomial f of x and if we put in a value alpha into it and it's equal to 0, then x minus alpha is a factor of f of x. We can find these roots and factors, find the roots and factors by trial and improvement. Just put numbers in until we get 0 come out. Or we could follow on once we've found one and using the grid method or algebraic division and the formula below to find what g of x is and then carry on for the lower and lower. So we start with x to the 5, then we go down to x to the 4, x to the 3, etc. Okay, hope that's of use.